So we're going to talk about this idea of how we use models to understand thinking, because one of the things that we're going to regularly do in organic chemistry is explore a phenomenon, whether that's a reaction or a molecule, and then we're going to construct a representation of that reaction or mechanism, and then we're going to look at the evidence that we have to support using that model. And so this idea is we're going to continually examine models by asking questions. And then we're going to think about what are the patterns or relationships in the data. And some of this we do as in-class work. Some of this is really work that we do to diffuse misconceptions or to resolve misconceptions. And then we are going to come to some type of consensus. And then we're going to look at our understanding of that chemical concept. And then you're going to be able to practice that through the homework and the readings that you do through this process of reinforcement. So we're going to refine and reinforce. And the goal of this is really to be asking, what's the purpose of this question? What am I supposed to learn? So for example, fundamental skills like identifying types of isomers, manipulating various types of chemical diagrams, being able to determine R or S nomenclature for stereocenters, and then identifying the stereochemistry of various reactions. We apply all of these skills to understanding reactions and mechanisms. So for example, are these molecules enantiomers, diastereomers, or are they the same? Take a moment, think about what you know. If you recognize that this was a molecule that had an internal plane of symmetry, so by internal plane of symmetry we mean right here, and thus it would be an achiral molecule incapable of having an enantiomer, great job. If not, you fell into the meso trap. The meso trap is a common feature on exams or tests to make sure that you understand the concept of chirality and that you're paying attention. So a meso compound is a molecule that has chiral centers, but it also has a plane of symmetry. So here's an example of planes of symmetry. They can cut through atoms and or bonds, and you can see from the plane of symmetry that both sides of the plane have the same constituents. So let's take a look. Are these molecules enantiomers, diastereomers, or the same? Take a moment. Think about what you know. If you can find planes of symmetry through bond rotations, so for example, here we rotate 120 degrees. Here we rotate 120 degrees, and then we rotate an additional 60 degrees. Or here we rotate 60 degrees. Then each of these, right, we could identify, right, as either meso or chiral. So here, right, a meso compound where this is R and this is S, and I have a plane of symmetry, the stereocenters are opposite, this would be an example of a meso compound. Here, where my substituents are arranged symmetrically, but the stereocenters are opposite, this too is an example of a meso compound. But by comparison, if I look here, this is a contrary case. This is where substituents are arranged symmetrically and the stereocenters are the same. This would be an example of a chiral or non-meso case. The other thing that we've been practicing is assigning priorities and then assigning R and S stereocenters. So you're going to assign 4 different priorities, highest being number 1, lowest being number 4, and then holding number 4 in a dashed or wedge, in a dashed position as opposed to a wedge. Then you're going to look at the substituents 1 through 3 and determine if they're moving in a clockwise direction or in a counterclockwise direction. And some examples are shown here. So this would be an example of counterclockwise, thus S, versus clockwise, which is R. So if we connect the groups in order 1, 2, 3, and the direction is clockwise, then the chiral center is going to be R. If the direction is counterclockwise, then the chiral center is S. Another way that you can do this is actually using the structure on the left. You can use your thumb. So your thumb is going to point towards the atom of lowest priority. If your fingertips point in the descending order, so 1, 2, 3, on the right hand, that indicates the R configuration. If you do this with your left hand, right, and you see that relationship 1, 2, 3, then that would indicate the S configuration. So if you want to, you have 3 different approaches now that you can use to determine R and S. Sometimes that lowest priority group is not facing away from you, so you have 2 options. You can switch any 3 groups and then just assign it as you normally would. Or you can switch any two groups, but when you do this, you have to actually switch your final assignment. So for example, if you swapped any two and then assigned it as R, it would in fact be S. Next thing that we're going to do is look at the naming of haloalkanes. So we have the parent alkane. We're going to number the parent chain just like we have for many other chemical compounds. And then we're going to look at what our halogen substituents are by the prefixes fluoro, chloro, bromo, and iodo. And we're going to list those in alphabetical order with other substituents. And then we're going to locate that halogen on the parent chain. So take a moment, go ahead and name these compounds. We're going to check your work. A couple of things you want to pay attention to. Remember, we always want to order so that we have the lowest possible numbers for our substituents. We also want to make sure that our names are in alphabetical order. One of the reasons why we're concerned about understanding haloalkanes and being able to name them is the fact that freons or chlorofluorocarbons, these CFCs are some of the most widely used. So freon 11 and freon 12, these are very common chemicals and unfortunately cause significant ozone depletion. And while there are alternatives, such as hydrofluorocarbons, HFCs, and hydrochlorofluorocarbons, HCFCs, it's important that as consumers we understand what choice we're making when we're choosing to use certain types of haloalkanes. So we look at haloalkanes because we want to be able to use these compounds to explore two types of reactions. So today we're going to learn about nucleophilic substitution, and we're also going to learn about beta elimination. So both examples are shown here. In nucleophilic substitution, a nucleophile, such as a ethoxide, attacks a carbon that is adjacent to or connected to a leaving group, such as bromine. That attack then displaces the bromine, the leaving group, and in place of the leaving group, we now have the nucleophile as the new substituent on that compound. By comparison, if we do an elimination reaction or a beta elimination reaction, then we have a base that is going to take the proton, so in this case, the sodium ethoxide functions as a base as well as a nucleophile. It takes the proton and then the electrons from that bond drop down, form a double bond, and then kick out the bromine. This formation of a double bond is what we call elimination. Now, I love analogies to help make sense of this, and given the cats that I have, these are particularly poignant analogies. So, if we take a look at these two examples, an SN1 reaction is what occurs when a cat leaves of its own accord, and there's a space now for another cat to occupy. So in this case, the cat is a representation of our leaving group, right? It also is a representation of our nucleophile. The empty bed would be a representation of a carbocation. SN2 is slightly different. In this case, in an SN2 reaction, I have a cat, in this case a nucleophile, that actively displaces my leaving group, in this case represented by the gray cat, to then occupy its position. So if we take a look at nucleophilic substitution, that's going to take place on an sp3 hybridized or tetrahedral carbon. And there are a variety of compounds that could be considered nucleophiles. Hydroxides, sulfur compounds, halogens, amines, water, methanol, ethanol. So it's important that we understand what these letters represent. The two processes can take place simultaneously. That's what we call SN2. So it's substitution, and it's nucleophilic in that it involves a nucleophile, but it's also bimolecular. So there are two chemical species, or two chemical compounds, that are involved in the rate determining step. So if I look at the rate is going to include both a haloalkane and a nucleophile. What does that look like? Well, here's an example of a mechanism. So I have a hydroxide, my nucleophile, as well as a haloalkane. These two interact. I have a transition state that I have simultaneous bond breaking and bond forming. And then I form my product by kicking out my bromide. So my hydroxide has replaced my bromide, and notice I have inversion of my stereochemistry. If I think about that rate, I can also make sense of that rate simply by looking at an energy diagram. Here are my reagents, here are my products. Notice the difference in energy between reagents and products. Also look at the activation energy that it costs to form the transition compound. So if we think about a different mechanism, this is where a bond breakage occurs, right? First, the leaving group is entirely gone, and the formation of a carbocation takes place. This is a mechanism designated as SN1, where the S stands for substitution, the N stands for nucleophilic, and the 1 stands for unimolecular. So only one species is involved in the rate determining step. And in this case, an example of that is the haloalkane. So if we think about a mechanism then, SN1 is illustrated by bromide leaving tert-butyl bromide. So I break a bond and I form a carbocation. I can do this because bromide completes its octet rule and it's a stable anion. Just like this tertiary carbocation is also stable, notice it's also trigonal planar or flat in the plane of the page. Step 2 is where a nucleophile then reacts with that carbocation to generate an intermediate. That intermediate then has a proton that's removed, where that proton transfer to methanol completes the reaction, and I'm left with an ether. If we look at the energy diagram for nucleophilic substitution SN1, what we actually observe is that there's 2 activation energies. There's the initial activation energy that's necessary to form the transition state intermediate, the carbocation in this case. Then there's also the energy of activation that's required to go on to form the products. So this is 2 stages, which is SN1, whereas SN2 is only a single stage. So when an SN1 reaction occurs to form from a secondary haloalkane, sometimes we're going to form a secondary carbocation. Now what's interesting about that is that if I have a methyl group or a hydrogen, it's pretty common to actually see a rearrangement to form the more stable tertiary carbocation. So for an SN1 reaction at a stereocenter, the product is a racemic mixture. And if we think about this, the racemic mixture is an equal mixture of both S and R. So we started with the R enantiomer only. Excuse me. We, through ionization or the loss of chloride, form a carbocation. Notice this is a secondary carbocation. Then our nucleophile can attack, but it can attack either from this side or from this side. And because it can attack from both sides, it can form both the S and the R enantiomer. So I want you to take a moment and evaluate the following questions. So these are questions that will help you think about your understanding of both the carbon-chlorine bond of the methylene chloride, as well as, of the methyl chloride, as well as providing an example of a mechanism, and then thinking about the reaction of this chemical compound with iodomethane. And it's also an opportunity for you to use a cat analogy to help someone understand SN1 and SN2. Next time, we're going to talk about substitution and elimination in significantly more detail. But here's a picture of where we're going and what it is that you need to know. This will give you a sense of the type of reactivity for methyl, primary, secondary, and tertiary carbon compounds. Thanks again. Have a great day.